Hi, now we have an example for multiple linear regression. So remember this data set. The response variable is price, and the predictors are square footage, year, number of bedrooms, and the number of bathrooms. So we can connect these predictors by plus symbol, and still we can use the same LM function as chapter 6. Then we can fit the result. We can get the results. And if you type summary of LM full, then we can get this. If we don't put summary, then we will get more basic results, not as detailed as this. Okay, so we will see the result. At first, residuals. So this is the distribution of epsilon hat, so the error term, so observed error terms. So the minimum and median, maximum, and first quartile, third quartile. So that is 25 percentile, 75 percentile. So mean of epsilon hat is always 0, so it's not reported. So median is negative 665. So probably this distribution is skewed to the right a little bit. Yeah, and coefficients, the most important quantities are here. So basically the price is equal to negative 1.5 times 10 to the power 6 times, this is the intercept, and the plus the 1.09 times the 10 to the power 2. So that is 109.4 times the square footage. And plus this is the 78.0 times year. And minus 8,837 times the bed. And this is 1.04 to the power 4. So 10430 times the number of bathroom. So this is the prediction model. So at first intercept, this is actually the negative $1.5 million. So, but it doesn't really matter. So it's just determined by other variables. So maybe you don't really have to care about it. So second term, the 109.4 times square feet. So one additional square feet means the $109 the more expensive. That is a kind of typical in the real estate market. So it sounds fine. Year 778 positive sign times year, because newer house is more expensive, right? So if 1 year newer, then $778 more expensive. And that is a small amount. In some countries, this amount is really large. For example, in Singapore, they rebuilt, they demolished the building every 20 years or something. So in the US, we keep the buildings longer. And here, the negative sign, the 8,837 times the number of bedrooms. So this is a kind of contradictive, but the more bedrooms, we have less value. Okay, so this sometimes happens just because of the technical reasons, but actually this negative coefficient is the typical. Why? Because we have included the number of the square footage and also the number of bathrooms. And the bedroom doesn't mean much. So the bedroom has just the 4 walls and maybe 1 closet and just a carpet. So if the square footage is large and just we have many bedrooms, so that means that we don't have many expensive features. So that's why that we have negative sign. If we don't include the square footage, don't include the number of bathrooms, then probably the number of bedrooms have positive sign. But here it's totally reasonable to have negative sign, because we have already given other information such as the square footage or number of bathrooms. And the number of bathrooms, we have positive sign. So to develop a bathroom, so we have to need the water line, and we need the sink, and we need a toilet, so we need drain. So it costs more. And generally, the more expensive houses have more bathrooms. So sometimes the expensive house have 8 bathrooms, while they only have it only has the 4 bedrooms. So it's totally reasonable. And the standard error. So this means how reliable this estimate is. So for example, think about the number of bedrooms. So at first, the negative sign is a little bit counterintuitive. And the negative 8837, how reliable this estimate is. Then standard deviation is 3.168 times 10 to the power 3. So that means the 3168. So somewhat large standard error, but at least the size of the effect is 8,837. So compared to this, the 3,168 isn't very large. So we can say that probably the bedroom is, so the negative sign is robust. So bedroom have the negative 8837, so 8,800 as a coefficient, and the standard size of error for this quantity is 3,000. So this coefficient may be 5,000, or maybe 11,000, but probably it's negative. And the ratio of these two quantities, so this is given by t-value. And basically, this statistic follows t-distribution with the degrees of freedom they're given here. So actually, this data set have probably 490 observations. And we have 5 parameters. So we subtract 5. Then we can calculate the degrees of freedom. And this ratio follows t-distribution with the df freedom 485 if the true effect of the bedroom is 0. Okay, so this negative 8,837 is the estimated effect. If truth is 0, then the t-value is distributed as the t-distribution with df 485. And here, the effect is negative 2.79. So basically, this t-distribution is almost the same as normal distribution when degrees of freedom is large enough. So this is really at the lower tail part. So it's significantly different from 0. And p-value, this is a two-sided p-value. So this total area is p-value. So p-value is 0.005. So we can say that the coefficient for the bedroom is significantly different from 0. And it can, so this explanation apply for other variables such as square footage, year, and bus. Intercept, usually people are not really serious to interpret this. Yeah, and the residual standard error. So this is the estimated sigma hat. And the multiple R squared. So this explains how much of the variation in price is explained by these 4 predictors. So if we add these 4 predictors, actually, basically this compares the variance of y and the variance of estimated epsilon. So this ratio, maybe to be exact, this ratio, 1 minus this ratio. So this is the multiple R squared. So that means these 4 predictors explains the 82.59% of the variability in y. And adjusted R squared, so we have the adjusted version. So adjusted R squared is basically motivated by the test. So if all predictors are, do not explain the response variable, so any of the predictors do not, contribute to explain the response variable, then adjusted R squared becomes 0. So basically, this penalizes the large model. So if we have more predictors, then we can it's possible that we can explain the response by those predictors by chance. For example, if we have 490 observations and we have just 490 different variables, then even if they don't have true, the true relationship with the response variable. They're still just by chance, if you just put the all predictors, then it looks like those predictors can predict response, right? So we would like to avoid that situation. So we penalize the large model. So if we have large number of predictors, then we have smaller adjusted R squared. And we have the 4 predictors plus intercept, so this number is smaller than multiple R squared. So if only one predictor, then actually these two numbers are the same. And F statistic. So this explains how well this set of predictors explains the response. And the p-value is very small, so at least this model is more useful than nothing. So it's more useful than the model with only intercept. Yeah, and these are the degrees of freedom to do this testing. Yeah, I would not explain the detail of this F statistic, but now that we have studied the all interpretation of the output at least. Yeah. And yeah, so yeah, so we have to be careful about this, the p-value, the test result, to see these variables are useful. And we have to be careful about what is the null hypothesis and what's the alternative hypothesis is exactly. And in the case of the bedroom, so we got the p-value of 0.005. What's the null hypothesis and what's the alternative hypothesis? And actually the null hypothesis is the model with all variables except for the number of bedrooms. And alternative hypothesis is the model with all variables, including the number of bedrooms. Means we assume that the square footage, year, and bathrooms are already in the model, and we would like to see if this number of bedroom has additional information to the base model H0. So if we have more variables in the model, it's harder to get the significant p-value. But the number of bedroom has additional information. Even square footage and year and bathrooms are already known. And the R has also the ANOVA function. So you can put just ANOVA, then the name of the LM model, the linear model. Then we can do similar test, but this is sequential. So why? Just the R is developed in that way. So sometimes we want to see the sequential result, sometimes the leave one out result. So ANOVA function, we compare the base model with the model with just first variable. Then model with first variable against model with 2 variables. Then 2 variables versus 3 variables. And the 3 variables versus 4 variables. So just sequentially, we add one more predictor. So sometimes we want to use it because certainly at first we want to think about square footage, and we would like to see if the year has the significant effect on the price when square footage has already been considered, and so on. Yeah, as we discussed in the chapter 7 in ANOVA, the balanced two-way layout, some specific case, actually the leave one out result and the sequential results are equivalent. So that means the predictors, 2 predictors are just not related to each other. So it doesn't affect each other. So here is the ANOVA result. So yeah. So remember that this is sequential result. And yeah, so at first, this is the residual. So we have the total size of the variation, that is yi minus y bar square and take summation over I. So this is the total sum of squares. Oh, sorry, this is sum of squares, so here. And the out of this, the total sum of square, maybe SS total, I would say, SSTOT. And the SSTOT is decomposed into several parts. So that is this part, the sum of squares. If we make the total, that becomes this. Okay. Then what these numbers explain. So at first, the SQFT. So if we include the square footage in the model, so that means the y is equal to beta naught plus beta 1 square footage, then error size becomes smaller. Okay, so if we don't have square footage, then basically the variance of epsilon is the variability of y, the variance of y itself. But if we have beta 1, the variance reduced, and how much it will be reduced, that is the sum of squares. So that is the portion of errors explained by the square footage. And the next one is the further reduction in variance. So this explains how much the second term reduce the size of epsilon. So if we compare these two models, the second model have smaller the variance in epsilon. So then reduction in the variance of epsilon, variability of epsilon actually. So we are not dividing by sample size. So that quantity is the sum of and so on. Then we add bedroom, the number of bedrooms, then the further variance will be reduced. Then the reduction in the variance is written here. Then the number of bathrooms. Then finally, the residual. So this is the variance of epsilon in the full model. I mean the sum of squares. So the sum of the squared residuals for the full model. Then now that we calculate the F value. Yeah, and at first we divide the sum of the square by the mean square. So by this degrees of freedom, then we get the mean squared. So actually the degrees of freedom is 1. So actually nothing happens, it seems. But sometimes if the number of bedrooms is a factor variable and the number of bedrooms have, for example, 5 levels, then we have the 4 indicator variables here. So in such a case, we have degrees of freedom 4. Then we divide this sum of square by 4. So we divide by this 4 and so on. Yeah. Then we compare the ratio between the square footage and the entire residual. So yeah, so the quantity divided by this quantity, maybe I would say that this quantity divided by this quantity is this. And it's known that under the null hypothesis, actually this F value follows the F distribution with the degrees of freedom, this and this. So F of 1, 1. Then actually the F of 1, 1 has typically the value around 1. So 2000 and the large value of F that rejects the null hypothesis of null model is, I mean the model with square footage isn't different from the baseline model, only with intercept. So the F value is large enough. So that means actually the square footage have very large contribution to reduce the error size. So the p-value becomes very small and very significant. Then same thing for other terms. So this term divided by the mean squared residual. So this comes here. And still this is very large. So 36.4. So this is significant. And others are the same. So this divided by this. then actually they're all significant. And the later variables, excuse me, p-values gets larger, so less significant. But that is natural because the square footage is considered first. So that means that we don't have any other information, and we compare. So we judge if the square footage is useful when no information is available. But for the number of bathrooms, actually we assume that these three variables are already available. Then we will see if the bathroom has additional information to these three variables. So it's more difficult to get the significant p-value, but actually everything is significant. So probably all four pieces of information are useful for this model. So if we change the order, the result will be different. So I just randomly changed the order, bath, bed, and the square footage and the year. Then actually they're all significant. But you can see that, for example, the number of bathrooms becomes more significant and the year becomes less significant. So the order matters for this table because the meaning is different. So this test is sequential. Yeah, so I explained how to do multiple linear regression in R, and also how to interpret the results in multiple linear regression.